This topic is UML, and I will try to tell you what UML is, what are its benefits. I will mention and describe some of UML diagrams and a little bit about design and school of thoughts behind UML, which is abbreviated as three-letter abbreviation MOF. So what is UML? UML is three-letter abbreviation coming from Unified Modeling Language, and it is standardized language adopted as international standard and managed by consortium called Object Management Group, or OMG, not oh my god, but Object Management Group. And it is standardized way how you visualize design of a system. And system may be many things, not only software. System may be technological process, system may be business process, and system may be some other thing. But we, in Java Bootcamp, of course, we will pay most of attention to the software and design of software. And in general, it doesn't force any particular design approach, but of course it's very friendly with object-oriented principles. And if you remember what object-oriented principles were, object-oriented principles are that you start with naming items and starting with describing these items, what are similarities and differences between them, and then you describe how these items interact each to other. So this means that UML is quite good to describe distributed systems and the interaction of distributed systems when you are talking about processes like braking car, mixing color, or some other very physical process. Then of course it may not be so good, because UML is good to describe discrete systems when you can pinpoint and point to something, this is this, this is that. But if you are talking about fluid mechanics, etc., then of course there may be other models to describe this process better. And UML is eclectic language, and eclectics in architecture means mix of different styles together. And before standardization of UML, there were different kind of graphical representations and languages of systems. One of early approaches were state charts, introduced by computer scientist with family name Harel. Then another was Booch, and name for Booch was Konrad Booch, which was one of the developers of other programming language. Then other computer scientists and project managers, Jacobsen, Coleman. So there was quite a lot of different notations and approaches how to describe systems. And in this case, all these systems are mostly software. How to describe software and how it works. But then, around 1990s, there was an effort to standardize these approaches and make them together. And so everything was collected together by this Object Management Group when it introduced Unified Modeling Language, where they took everything good from these other notations and languages together. And first real version of this language was introduced in 1997, so before year 2000. And when I studied for my master's degree and for my doctor's degree, that was around year 2000, I did my small contribution to this standard as well, to analyze and describe better UML version 2.0, which was improved version of UML 1 point something. And later, around the year 2005, maybe later, there is another modeling notation called business process modeling notation. It developed mostly to describe business processes, not software. And around the year 2007 something, this notation was also adopted under, responsibility of OMG. And they also standardized and described BPMN and UML and how they are similar each to other. And I did some small contribution in this standardization as well. And what are parts of UML standard? So there are 4 important parts of this standard. You are mostly interested about UML superstructure. So infrastructure, if it's building, it's underground and somewhere inside. Superstructure is what you see. Similarly to ship, infrastructure is behind water or below water, and superstructure is on top of water, on top of body of the ship. So if you are just user of UML, you are mostly interested about superstructure, which describes UML for its users. If you also work in modeling tools and more detailed system design, etc., then you may be interested in infrastructure in UML itself. And in more details, you may be interested about object constraint language, which is standardized language how you describe constraints or precise relationships between different objects from the classes. And also, if you are working with different tools, UML diagram interchange standard describes how can you import, export UML diagrams from one tool to another. And source for UML, last time I checked this version 2.4.1. And superstructure is approximately 600-700 of pages. These other are a little bit less. What are main benefits of UML? First, it is graphical language. And why it's important? It's important because we have graphical coprocessor or graphically accelerated parts in our brain to understand pictures and analyze relation between these pictures. And we have developed this possibility for billions of years in many different ways, like insects do this differently than octopuses, which do this differently, little bit differently than birds and than animals. But if we see picture, we can understand important parts of it much quicker and much easier than reading text. Text is very precise, but problem with text is that relation between concepts and what you see as a picture is quite complicated. You need to understand what character is, you need to understand how these characters are grouped together, what this word means, etc., etc. And there are still quite a lot of people which are not good at reading and writing. I myself, I read, write quite easily. Writing is not easy for me because I have sloppy writing. I, for example, usually mix numbers inside, digits inside numbers quite easily. But so it's not so easy for humans to understand text. And it is platform independent, so you can use UML to describe different kind of software using different kind of programming languages and tools. It is standardized, so it is adopted as international standard. And if you learn UML in Latvia, it is the same UML what you can learn in China, India or USA. And UML, similarly to writing, is very precise. So when you draw some pictures, when business people draw pictures, usually these are not very precise pictures, and pictures lose some meaning in difference with text. But UML is very precise language, even if it is graphical language, so precise that you can create system design and execute your system just by drawing picture. So every element you draw has very precise meaning, and if it's precise meaning, you can create software out of this picture. And this allows you to use UML not only as a documentation, but also as a part of your building process, as a part of your system design. And here is shown class diagram, which shows most important UML diagrams. And this arrow means extension, and there is concept, which is abstract concept, just a diagram. And these diagrams are split into two parts, structure diagram and behavior diagram. If some of your colleagues is old school UMList and he or she learned UML, let's say 10-15 years ago, he or she may talk, or some designing tool might talk about static structure. And static structure was used to name these diagrams in UML version 1 point something. And static means doesn't change during time, in simple terms. But they didn't like this term, and therefore these were renamed as structure diagrams, and they represent what is not changing, what is always true or invariant during time about your system. Most prominent diagrams are class diagram and package diagram, but if you need to describe deployment, how you put it in distributed system, you use deployment diagram. Composite structure, for composite structure profiling, to profile or extend and modify diagrams, and component diagrams. And object diagrams describes system in runtime, how it looks like when it is working. This is another comment in UML. And then there are behavior diagrams, and behavior diagrams are at least two different types. Some diagrams shows time explicitly, like on X or Y axis, so you can calculate time very precisely. For example, for sequence diagrams, timing diagrams, etc. Some of these diagrams show time implicitly, like state machine diagram and activity diagram using dependencies. So you do not know precise timing, but you know precisely sequence of events, how it happens. And some diagrams do not care about time at all, like use case diagram. And most important for developers probably is this static or structure diagram called class diagram. And class diagram shows very precisely with one-to-one relationship your object-oriented code and picture into class diagram. And class diagram is used to show design of your system, describe responsibilities of parts of the system, and can be used for forward and reverse engineering. So you can create your system from your class diagram, or you can do class diagram from your system. So forward means from plan to actual structure, and forward it's old school engineering, what you do for buildings, bridges and cars. So you start with plan, then design, then implement it. And reverse engineering is, if you look on real-time world, some Chinese company buy Mercedes, then dismantle it, analyze it, create plans for it, and creates clones of Mercedes with some different name for this Chinese company. And because of intellectual properties and other laws which makes life for big monopolists easier, in many cases reverse engineering is illegal. Similarly, if you use Microsoft Office or Microsoft Windows as a already compiled and packaged binary application or system in general, then one of things you agree in end-user license agreements is that you will not reverse engineer this system and you will not use their knowledge in your own tools. So because of that, forward engineering is better supported by different tools and utilities. Reverse engineering usually is supported and provided by different kind of educational institutions like high schools and open source communities. And here is example of class diagram. Large boxes represents classes, and then there may be one or several parts of these boxes called compartments. In first compartment, which should be always there, is name of the class, and then second compartment is list of properties, and then third part is list of methods. And syntax is that similarly to more modern programming languages, name is first, type is second. So you first name this variable, then you say what the type is. And then you can draw different kind of lines between them. And theory behind class diagram is graph theory. And that's one of reasons why UML is so precise, because they have very proper meaning, and this is just a graph. So here you have nodes connected with different kind of edges. And these edges can be different types. One is just a line. Then this means that instances or objects in jargon of this class are somehow related with instances of that class. You can add object constraints in OCL language. For example, you can say one object from this class is related to many objects from that class. You can add arrows here. This means navigability. This means object from this class will have direct reference to object of that class. And that means that order actually will contain a reference to customer. This means inside body of order class will be variable called, let's say, customer with type customer. And then there are generalization or specialization. This closed-ended arrow look like triangle. So this is open-ended arrow and this is closed-ended arrow or triangle. So this shows that this is more general class and this is more specific class. And then you can put generalization, specialization in tree-like structure. You can join them in T-junctions. And last time I checked, like Microsoft Visio does show junctions something like this. Here is one class, here is another class, here is association, here is one class, here is another class, and here is association. So if you see something like this and something like that, this is improper usage of UML standard. Like this is just a two-level road, not actual junction, and this is junction. So I call this approach, I can't draw UML diagrams properly, because if you do properly, and UML diagrams are not first diagrams what computer scientists and engineers in general have used. Before UML diagrams there were electrical diagrams and network diagrams for electricity network, etc. And there is very old convention here that proper junction is always T-junction. And if you have these four classes and you want to join them properly, you create two T-like junction, T here and T here. That means, and some good tools even did make navigability easier. They did something like this, so you know where other end is connected. But it's not required. Important is that it is T-like junction. And if it's just cross, it means it is just cross, is not a real junction. So that would be, so if you do this, you again, formally you may be right, it may be readable, but proper approach is use T junctions for junctions, and X means just a cross, it doesn't mean actual junction here. And also UML allows multiple inheritance, so you can easily create diamonds of your inheritance if you wish, because class diagram do not care about implementation, it cares only about design. And so simple and detailed association is simple line. Open-ended arrow means that you have direct reference to other end. And then there are diamonds. In Latvian, diamonds are called as rhombs, not caros or whatever. And these diamonds may be two different styles, colored and uncolored. Colored means that these things are essential part of this thing. For example, how we built our amphibia or Frankenstein monster. If body, legs, arms and head are essential part of human, then we make them as a colored diamond. And composition also may be shown as a T-like structure, similarly to generalization, specialization. You may have T-like structures, and this is a closed arrow and these are rectangles. And similarly for composition or aggregation, you may have joined everything together with these T-like rakes or junctions. So if this is not colored, it is just aggregation, and this means these are not essential part of that thing. This means this thing is just something like container where you can put different objects. But if it's essential part, it is colored, and that means if some of this part is missing, if it's mandatory of course, then all these parts should be together to create this particular object. And here example is, for example, a carburetor is essential part of some old school car, but docks are not essential part of pond. There still can be valid ponds where there is no any dock inside it. And here with OCL you write ranges of minimum and maximum. So there may be free floating carburetors which are not put into car, because there may be carburetor where there is no relation to car at other end. But if there is, so that means there may be 0 cars related to carburetors. But if there is one car related to carburetor, then there should be one and only one carburetor for this particular car. Of course, it's not true in real life. There may be 2 carburetors or even more in some cars, but that's what this diagram says. And here similarly, lower range 0, upper range 1, lower range 0, upper range anything. And you can make it as a shortcut notation, use only star for it. So 0 ... star is the same as just a star in OCL. And then what I have not mentioned here is dotted line or dependency, not dotted line, dashed line. For example, class, other class, dashed line, open-ended arrow. So this is dependency. And for practitioners, one of the dependencies may be if it's interface and this class implements that interface. And again, if you draw this diagram properly, dependency is a dashed line, not dotted line, and with open-ended arrow. And then important thing is that there are two different graphical notations for the same thing. For example, we may have car and carburetor. And we can show it, in general we can show it like this. But then we can say that it's also diamond, and you can do this in more detailed thing. Diamond open-ended arrow, this means this is an essential part of that, this has direct reference to that. But you can also rewrite it in different way. Car in such way. It is absolutely the same, only difference is how much details you have, because if you put it as external class here, you can always have other compartments for properties and methods, but if you put it here as a complicated attribute inside car in this class, you are not able to explain it in more details here. So this is short notation and this is detailed notation. And if you say what name here is like carb, then of course you write carb column carburetor. So this is name of your variable and this is type. So these two are equivalent in meaning but different in details, how much details you show in your graphical picture. So, and then even though UML is graphical language, standard describes everything in black and white. So only thing where you talk about color is colored or not colored. But UML allows you to extend this standard into different styles. In old school UML, these were called stereotypes, and stereotype is quite simple thing, it is tag. Like we added this tagging interface, we may say that this car is, I do not know, interface. And this is just a tag. You can add tag to everything you like, and for example for dependency here, you can add tag implement. But starting with UML 2 point something, instead of the stereotypes, they renamed them profile. And again, why do they rename stereotype to profile? To force your attention that profile is something different than stereotype. If stereotype was just a tag or label, then profile is still tag and label visually, but profile also says how can you expand meaning of UML for some very specific reasons, for reverse forward engineering, for simulation, etc. So visually profile is just a tag, you still can say it is interface. But with profile you can say that if you see this particular tag, for example you generate source code which is not class, let's say here, instead of class AAA, you generate source code which is interface AAA. And of course these two things are completely different. And again, if somebody still talks about stereotypes, then he or she has not updated his or her knowledge about newer versions of UML. And similarly, many of tools I have still checked talk about stereotypes, not about profiles. And then use case diagram is behavior diagram, but it doesn't care about actual behavior. It actually cares about who does what and responsibilities and roles. So it is a graph where nodes are represented either as ellipses or stickman, An ellipsis shows important operations called use cases in your system, and stickman represents users of this system. And if you work in system integration and system automation, external system is also sticky man, not your use case. You draw use case diagrams only in early stages of projects when you just need to count responsibilities. Who does what, how it's related, etc. And so this is package, and this is your system boundary, which shows your use cases. And here you see another thing, for example, extension for serve food to serve wine. Again, in general, it's just a dependency, but in this case, dependency means specific extension of these use cases. And then with these lines you show who use what and who does what. And then for you as a developer, probably more important is sequence diagram. And sequence diagram is not graph, because in graph you always connect nodes with edges, but here you can connect line to the line. But in sequence diagrams, this is one of these behavior diagrams where time is explicitly shown and very precisely. Time flows parallel to these lifelines. And this is actually object diagram, which means that there is unnamed object with computer type, and here is unnamed object with server type, and they live from here till to here during time, and something is happening during this time on computer, and something is happening in these slices of time on the server. And if interaction goes immediately, then you write these lines of interaction orthogonal to the lifeline, but you may also force attention of somebody that it actually takes time, and then you draw these lifelines and interaction as a sloped line. So then you exactly see that interaction of sending something from here to here used so much delta time. And then you may show explicitly where some process starts with colored circle as a starting point. So checking email starts here. But you can also do this implicitly just by showing in time something starts here. So sometimes you need to add something like this if you want to generate code out of these diagrams. So you need to make them more verbose, more explicit, otherwise these tools do not know what to do. And then what is important, if this line is solid here, then structured data are sent from one place to another, and in this case structured data is something like email. And if it is dotted line, then it is single bit sent, like true or false, yes or no, done, not done. And then if this arrow is closed and colored, then this means synchronous operation. And synchronous operations means following. If you have lifeline of two things, and one thing calls synchronously other thing, nothing will go forward on this thing until this process will end. So it will wait for it to end, and only then this process will continue. So this is synchronous. But if this arrow is open-ended, this is asynchronous call. You do call something on server and forget about it, and this process here locally continues. And usually if you use web application and web frameworks, usually you want to get asynchronous callback to see that this process was actually done. And how it looks like in simple web applications. Not in this, probably in the... So we can edit some page. And we can save, and this saving, as in many web applications, is done is asynchronous call. You can still continue, for example, save, and see you can continue. And after that, we got this callback back here, and it's shown as a message that this particular page was saved. Very widely used system design approach, asynchronous calls with callback. And so told about this, and then about these rectangles. So rectangle shows how much time some process is taking on one or another lifeline, and you may make sub processes inside processes of these sequence diagrams. For example, you can put a rectangle on top of a rectangle, something like this. Or you can do different alignment, something alignment just to one side, to say that there are some sub-processes of process. So this is sub-process of this larger process. If you put rectangle on the top of other rectangle. And in short, that's it about sequence diagrams. So next one is state machine diagram. You may see state machine diagrams quite a lot. Theory behind it is graph theory and finite state machine theory, which is also related with Turing machine. And if you do not know what finite state machine is, or Turing machine, in general, this means everything which can be described as an algorithm might be described with this or this. Only difference is that Turing machine is potentially infinite, because finite state machine usually is represented as a state machine diagram. You have ellipses for states, and then with these directed edges you show how state changes, and you always have numbered account of these states. But Turing machine is just read-write head with potentially infinite tape. And you can read-write, and on conditions what you have read, you can jump to other place of tape in one direction or another, and again read and write. And depending on what you are reading, writing, it may be single bit, it may be character, it may be byte or whatever. And so this is how Turing invented this general purpose computer with read-write head and potentially infinite tape. And this is how it can be represented as a state machine diagram. And here is another example from UML standard. You can draw these boxes inside boxes. Then this larger box is something like pseudostate, which consists of several related actual states. And so these boxes should be with rounded rectangles. Sometimes you draw them as ellipse, but properly following standard, it is boxes with rounded corners. And in top you write what is state. If you like, you may say what are pre and post conditions to enter and exit this state. And then with these directed lines you say how can state be changed from one to another, and you can also describe what kind of event is causing change of state. And then you may explicitly show initial states with this initial starting point, colored circle, and you can show where it is finished with bullseye or colored circle inside another circle. And if it finishes with bad state or aborted state, it is circle with diagonal cross inside it. And in short, that's it about state machine diagram. As I told you, everything you can describe as an algorithm can be described as a state machine diagram or Turing machine. And problem here comes with distributed systems. For example, simple distributed system is client and server. And you can describe it as a Turing machine or state machine diagram, but then you have to describe it as a large machine where both clients and servers are inside it. And probably from here, and this is just bad abstraction, how can you describe these things? You can describe it, but it's not good way. And probably from here comes this misleading idea to tell that the internet is biggest machine in the world. Of course, if you want to describe entire internet with millions or billions of computers connected together, with state machine diagram, you have to draw border around all these computers, because with such abstraction, with such means how you describe things, this is only thing how can you describe computers connected to the internet. And then of course you have this large virtual finite state machine which does everything together. But of course such abstraction is bad, because everybody who knows something about systems understands that the internet is not one large biggest machine in the world, it is a set of many quite independent machines. And how can you avoid this bad abstraction? You can avoid this bad abstraction with different diagram introduced in UML 2.0, and it's called activity diagram. And graphical notation for activity diagram is absolutely the same as for state machine diagram, and it's also based on graph theory, but precise meaning, how does it work, what does it mean, comes from theory called colored Petri nets. And what are colored Petri nets? Petri nets are graphs somehow connected together, so nodes connected together with edges, and through these edges different colors of tokens are transmitted. And these tokens with unique color means unique type of data and unique value of data. And you send tokens from place to place. And if these tokens are the same, this means the same duplicate of the same data are going concurrently or parallelly through this edge and through that edge. And such diagram very well describes distributed systems, so much more proper description of entire internet would be to not draw one very large and complicated state machine, but to draw activity diagrams, because now here each of these boxes with rounded corners represents separate system which does one particular thing. And in this case, it describes some kind of workflow to handle orders. So it also is widely used to describe business processes. So you start with structured data request order. So here is your object. Then you handle it in one place, receive order. Then you decide is it rejected or accepted. If it's accepted, you fill this order. And then you start concurrent execution. One copy of order is shipped to the customer, but other is used to create invoice, to send this invoice, to make payment, to accept this payment. And when both of these things are completed, so request is shipped and payment is accepted, then this process is considered done. So here parallel execution is finished and you close order. Or if it's rejected, you just go here and close order immediately. So here is explicit start point also, and explicit final point as well. And here, if you describe it as a colored Petrinet, you have some unique color of token which goes either here and here, and here this token is duplicated. And when both colors of token are merged together here, these are joined together and it continues. And what is important here is that this is node, 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 this is node. So a node means box, large or small or whatever. And this is not line connected to the line. It is box connected to the line. Only difference is that this particular box is very wide and very thin or shallow. But it's still line connected to box, box connected to line, and box connected to the line. So that's about activity diagrams. And if you put activity diagram together with deployment diagram and other things, you can generate executable code for large complicated workflow management systems which runs in distributed systems for large companies. For example, to generate executable code for state machine diagram, this is quite well known business, and you can get quite cheap, maybe even free tools to generate some source code which will behave and which will execute this particular state machine. And for example, in most of cases for your kitchen appliances like freezer, microwave oven, actual oven, washing machine, toaster, etc., probability is very high that these manufacturers to implement them do not write textual code, but they write state machine diagrams to describe how this thing will go, and then generate executable code out of it. For example, elevators are usually described in the same way, and infotainment system for your car, and for example car which checks doors are open, closed, etc., etc. So when I was active in this area, I participated in conferences. One of BMW guys described how they use state machine diagrams to generate source code for BMW cars, and of course test automatically that these diagrams are correct and implementation is correct. But when you talk about distributed systems, then at least few years ago, when I studied for my doctor's degree, this was rocket science and it was very expensive. Only SAP, IBM could afford do their investigations and studies to make such systems that the distributed system is working and is generated out of simple business diagram. And I think still you can't get free and cheap tools For example, to generate executable code for distributed systems like using activity diagrams. But if you are interested about this and business process automation, this is one of studies you should do because thing is that this picture is understandable by business persons, and business persons will immediately see if your diagram shows this business properly or improperly. If you will show them your source code, almost nobody will understand is the source code correct or not. And so that's about forward engineering from drawings to the systems. And also, if you are working in business process management, business process automation, you should also check out BPMN diagrams, because BPMN diagrams are more expressive, and expressive means you can tell more saying less. And for graphical languages, expressive means you can tell more drawing less complicated drawings. So we proved in our studies that similarly to these equivalents of state machine diagrams of Turing machines and state machine diagrams, finite state automata and Turing machines, these are equivalent, only different description. Similarly, BPMN is equivalent to activity diagram, only difference is how expressive they are. And activity diagram is less expressive, so you need to add more details to say the same amount of information in UML activity diagram as you can say in BPMN. And now a little bit about UML itself. Why it's also very important to know UML is their idea about abstraction and reflection. And you may have heard something about reflection already, but in programming languages or in languages in general, reflection means that you can use language to describe language itself. And all human or people languages are reflective. You do so-called bootstrapping process. You start with very simple concepts and then you extend them. So two important concepts, bootstrapping and reflection. Bootstrapping means how you start from nothing and add more and more knowledge until you have enough knowledge about something. Bootstrapping is important when you start your computer. Bootstrapping is important when you start new programming language and write compiler or interpreter for it, etc. And reflection is important how you describe these terms and how you collect this information. And for any human language, you can do bootstrapping process and you can use reflection of the language, because you can learn Latvian using Latvian itself, you can learn English using English itself, you can use Chinese using Chinese itself, and you can bootstrap it differently. You can use Chinese to learn English because you know Chinese better, so you do this bootstrapping from something else. Similarly, when you write your initial version of compiler, you can use, for example, I do not know, Pascal to create C compiler. But then when it's created and it works, and the C compiler of course compiles language of C, then you can create a C compiler in C language and you recreate everything in C. But there are more primitive languages which are also reflective, and from textual language, very prominent example is BNF, where BNF means Bacchus and Naur, and Bacchus and Naur are two computer scientists which develop a textual language which is short and reflective. And here again you can see also how bootstrapping works. I don't know much about things except knowing characters and English. And I see here that there are some words because I know that words are separated by spaces. And I start reading something. That syntax of BMM consists probably of rules or rule and syntax after that, name of rule and syntax after that. And I also know, for example, that this pipe means or. And what is rule? Rule is optional wait space, literal value. So I also know that literal value means here already. Is smaller than, name of rule, larger than, optional wait space, this assignment or equals operator, optional wait space, and some expression. And what is optional wait space? Either space or nothing. What is expression? Expression is list or list, literal pipe value, and expression. And line end is either optional white space end of line or line end and line end. List is either term or term optional white space and it's list. And term is either literal or literal value of smaller than, name of rule larger than. And literal is either double quote text, double quote, or single quote text, single quote. And then I can read it again, so I know better what syntax means. That syntax is either rule or name of rule and syntax. And so with second iteration I have pretty good understanding what BNF is. And here is BNF used to describe BNF itself. And BNF is very widely used to work with compilers, interpreters, and other things. So you can use BNF, for example, to not only describe BNF, but to describe BASIC, to describe C, to describe Java, etc. And similar approach, but only difference is that it's for graphical language, is used to describe UML itself. So UML is reflective graphical language, and if you will study UML standard, you will see that there is a lot of English text around these pictures, but actually if you understand what picture means, you can learn UML only using UML itself, and you need this English only to bootstrap your process of understanding, because if you don't know anything, then of course you can't understand what picture means. And particularly for UML, to use this reflective process, they have very rigid and precise meaning what instance is. And here in UML they always talk about instances, because if you do not talk about instances, then problem is following. That there are two important things. Let's introduce mine here. So there is also a class called class, and we can go to declaration of this class if we have Java the compiler. And there is class called object, and it's also the class. And here these practitioners who are programmers exchange meaning of instance and meaning of object in the same way. Something like we have class customer, and object of this class customer is this particular thing. But in general what is happening there is following, that we have class called class and we have class called object, and these both are classes. This is class, okay, let's write it in Java. This is class and this is class. These both are classes, but what this is regarding to this is that object is instance of class How can we write it? Okay, I will write it following. And what does it mean? This means you use this class as a template and as an abstraction to create data structures, to refer to methods, etc., to create something. So class in this case is your receipt. And in jargon again you can say template, to create instance. And the instance of something, of course, is not the same as like extends or just object. So what we usually call as an object, precise meaning of usually it is instance of. But in UML they are very precise. When they talk about instances, they say it exactly and precisely. This is instance of that. And how does it work? So here again we do either management or simulation, and there is no difference between management or simulation. If simulation is very good, then you can say that what you have simulated in your system is actual management of your business processes. And if you have some business process of renting DVD movies, then you have some real world phenomena, and these are this meta level of abstraction layer in real life called M0. So here you have your DVD discs, and every time you rent them, of course, you could get your current situation just by calling all your customers and asking, do you have this movie Casablanca at your hand? Oh, you doesn't have. Okay, I will ask next one. And that would be very stupid. What you do, you create your virtual reality as an abstraction of this real life object, and inside your system you create some data entry about this movie, and then you describe it. For example, title is Casablanca, and then if you rent it to customer, you also assign virtual object to this customer. And then of course you can describe all this design, if you take about structural part, as a class diagram. And then you will see that you have different kind of classes, and these classes will have instances, and this is class and that is class. This is something like class, and this in Java would be object, but in UML it is class and instance. And you create instances of this class using this class as a template to know what relations are, etc., etc. And then funny thing happens. So you have described one particular process, you described how this look in more general terms, and then you can describe these processes using different processes first, and then not only renting books or DVDs, but buying, selling things, etc. Question here arises, what do you need to describe these many models and many different business processes which are completely different in details? And with this rigid idea of reflection, that this is just instance of that, you can say that in general, independently on any business process you describe, a model of this model will still be class diagram, if you, of course, if you care only about structural part. And this means that this class and that class is actually the same. So only difference is that in a real model there will be some classes which are instances of that class, and then there will be some other instances of that class as well. And that means that you don't need any other modeling language, you don't need any other more concepts to describe any possible model in the world. You can model business processes, you can model BPMN, you can model UML, you can model programming languages like C, Pascal, Java, Python, Ruby, etc. And everything, when you care about structural part, will be just different kind of classes and instances of these classes and instances of these classes. And so here is UML shown as a class diagram describing UML itself. And again, class diagrams represents only structural part of this static part, not behavior. But if you look on this structural part of UML, then everything in UML is just an element, and this is abstract class, as you can see. And some of elements may be comments, that's easy, or they may be named elements or relationships, which are still abstract. And relationships may be either direct relationships like generalization or dependency. So this is generalization, and dependency would be dashed line with open-ended arrow, or association. And usually relationships are shown as lines and elements are shown as boxes. But if you know something about graph theory and you create something like this graph, so this is node, this is node, this is node, this is edge, this is edge, this is edge, or box, 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 line, 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 you can always add or split these edges in part and introduce new nodes, and you can rewrite this particular graph that this line is represented as a box, this line is represented as a box, this line is represented as a box. And then you can redraw that these virtual halves of lines and boxes are represented as a line. This is represented as a line, this is represented as a line, and these two graphs are equivalent. You can transform from one to another, but what was dot here becomes line, and what was line here becomes dot. And similarly to UML, because it is based on this graph theory as more general theory, as I told, it usually shows that relationships are shown as lines. But it may be transformed and described differently, that relations are actually boxes and named elements are actually lines. For example, for these sequence diagrams where you draw lines and lines, etc. And then named elements may be namespace. In one concrete space, namespace is, for example, package or redefinable element. And then you see diamond here, multiple inheritance, that associations are also classifiers. And what is classifier? Classifier is redefinable element, which is also namespace, which shows relationship. And here is feature, and for example UML profile is also a concrete subclass of this feature element. So feature is some redefinable element you can add to the class. Of course, you can see here that every class here except comment is abstract. So that means you need to go in more details to see how it is organized deeper till to concrete classes. But if you look on general picture here, then this is UML described using one single class diagram, which is UML itself. And here are more details, for example, what classifier is. So this one here, to see actually concrete classes. The classifier, for example, is class, which may have parent, which has attributes and operations may have parameters, but I will not go in more details here. So, any questions or comments regarding to this topic?